In this lecture, we are going to do code preparation for our linear classification script. This example will look at a new classification dataset, so this lecture will go over loading the data as well. To recap, here are the general tasks that we need to complete. Number 1, load in the data. Number 2, create the model. Number 3, train the model. And number 4, evaluate the model. Let's start with loading in the data. For this example, we'll be looking at the famous breast cancer dataset. This dataset happens to be included as part of the scikit-learn API. You'll notice that in this course, we'll be looking at quite a few pretty famous datasets. These datasets are so famous that they are often included in various machine learning libraries, so there's no need to download the dataset as we did in our previous example. Of course, there will be plenty of examples in this course where the data do not come from libraries, so you'll get experience with each. Loading in data from scikit-learn is super easy. We just call the function loadBreastCancer, which returns a data object. This data contains the x's and y's, so we'll need to access them using the object's attributes. In particular, the inputs can be accessed using the data attribute, and the targets can be accessed using the targets attribute. There are two ways we'll want to pre-process the data before using it. First, the data isn't normalized. You already learned from our earlier example why this is a good idea if you did the exercise I suggested. Therefore, we will use the scikit-learn module standard scaler to normalize it. Second, we'll want to split the data into train and test sets. Intuitively, this is because we want to get a good idea of how the model will perform on data it hasn't seen before, not on data it has already seen. For the data we've already seen, we already know the answer, so machine learning isn't necessary. The data we really care about is the data we have not seen. For example, if you build a fraud detector, you want to be able to ask your model whether a new transaction is fraudulent. This is important because your model might do very well on data it's already seen, but poorly on data it hasn't seen. We'll discuss this more in a later lecture. In any case, this code shows you how to do both of these steps. Notice how we already used this idea of train test splits with the standard scaler. We fit the standard scaler on the training data only, and we apply the standardization on the test data using the fitted mean and variance of the training data. Once we've prepared our data, it's time to build the model. As you know, the linear classifier is almost the same as linear regression, just with one extra step, the sigmoid. This should be a hint that we're still going to have a linear object somewhere in the model. Well, it just so happens that the sigmoid is also represented in PyTorch with an object, the sigmoid object. It should make complete sense then if we combine the linear object with the sigmoid object in sequence. And in fact, that's exactly what we've done. PyTorch allows you to easily stack these computation steps in a sort of a wrapper object called sequential. What you're telling PyTorch is, I want my model to apply these functions in this order. And the functions we want to apply in this case are the linear model, then the sigmoid. There's one detail here that I want you to notice, and this is that when we create the linear layer, the input size is d, while the output size is 1. As you recall, our data matrix is of shape n by d, where n is the number of samples and d is the number of features. So we'll have one input for each feature column in the dataset. In addition, we have one output, which represents the probability that the output should be classified as a 1. The next step is to train the model. As promised, we are still doing gradient descent, which means nothing about our gradient descent loop is going to change. We still do our zero grad, get the output, calculate the loss, call backward, and do one step of a gradient update. What's different is that we'll be using a different cost function, but also a different optimizer. As mentioned previously, our loss function for binary classification is the binary cross entropy, which is performed in the object BCE loss. In addition, we'll be using the atom optimizer, which has become the go-to default in deep learning in recent years. Normally, I would say that the gradient optimizer you choose is like a hyperparameter, so you should always experiment to see what works best. In practice, many people simply choose atom by default. This does not mean that Atom is actually guaranteed to work best, so you should still try other methods and observe the results yourself. If you want to learn more about Atom, you're encouraged to check the in-depth section of this course. And if that's still not enough, then you'll want to go through the in-depth course where I discuss this algorithm in detail and build it up from scratch. The last thing we're going to do in our script is evaluate the model. This is different in classification compared to regression. In regression, we use the mean squared error as our loss, but we also use it as our evaluation metric. It kind of makes sense, since I don't think any other metric would be significantly more advantageous. The mean squared error is kind of a natural way to look at the regression error. Alternatively, you could look at the root mean squared error, which is just the square root of the MSE, so that it's in the same units as the target. But still, taking the square root is kind of a trivial transformation. With classification, it's a different story. We have the cross entropy as our loss, which is not a natural or intuitive measurement. What we really care about is accuracy. Out of all my predictions, how many did I get right? And how many did I get wrong? So in order to evaluate our model, we're going to calculate both the train and test accuracy. This necessarily also involves making predictions with the trained model as well, so we'll learn how to do that too. Of course, it's not so different from how we make predictions with our regression model. We'll just need to round our prediction to 0 or 1, since the targets are encoded as 0 or 1.